Okay, so today's lesson is going to be on our kinematics equations. We'll show you how to derive them and then also how to apply them to some problem solving. Okay, so at this point we've derived some equations from lab exercises. So we have our average velocity being our change in position divided by time, and our acceleration to be our change in velocity as a function of time. Now, if we have uniform acceleration with our speed changing at a uniform rate, we can also find an average velocity by taking the final velocity, adding the initial velocity, or the v sub 0, and dividing that by 2. That's the same as taking two numbers and finding the simple average of the two. If we rearrange this equation, we can actually form the third equation in your reference tables. A change in velocity is the final velocity minus the initial velocity, and then we divide that by the time. Now, if I cross multiply by t, I get AT equaling v minus v naught. And then I could add the v naught over and flip sides. So we get v equaling v naught plus AT. So this is just a rearrangement of the equation that we derived from our fan cart lab. Now, any sort of problem solving, we want to use these 5 steps. Okay. First, you have to ask yourself what is being sought after. So, in other words, what is being asked. Then you're going to be writing down the information that is given, okay, and list each one individually. Then find an equation that relates what is given to what is asked, and then plug and chug. And the important thing is that we want to put in the correct units for our variables that are given, and then reflect. A lot of the time that we can see an answer that doesn't seem reasonable, and I will do my best, and so will the AP and IB test, to make answers sensible. So let's try that out on a problem. We have a sailboat moving north at 7.5 meters per second, and we have a strong wind in the opposite direction, hence south, and accelerates the boat at a rate of 2.3 meters per second. So how much time? So the first thing that we're asked is to find the time. Now we're given the initial velocity, so that's the v sub naught, and I'm going to make north positive. So this is a positive 7.5 meters per second. And we want to know the wind, the acceleration is in the opposite direction, so this is a minus 2.3 meters per second squared, meters per second. So we also know to bring the boat to rest. So the final speed is going to be 0. So that's not a number that is in the problem, but it is implied in it. So we have v equals v naught plus AT. Cross off anything that's 0 right off the bat. So I have 0 equals v naught. I'm going to subtract v naught from both sides. So I get minus v naught equaling AT. And then the last step, in order to find the time, I'm going to divide by A. So that gives me t equals the negative of our initial velocity divided by our acceleration. And so we get a negative a positive 7.5 meters per second. And then we divide that by negative 2.3 meters per second squared. So if we look here, we get a negative divided by a negative, which is a good thing because we should always end up getting a positive time, because a negative time doesn't make sense. And if you do 7.5 divided by 2.3, you get 3.3 seconds. And once again, that seems reasonable because this is slowing it down at 2.3 meters per second. So after 1 second, it's going 7.5 minus 2.3, or 5.2 meters per second, 2 seconds, and so on and so forth. And finally, it's at rest at 3.3 seconds. Now, if we want to know how fast the boat is moving after 6 seconds, well, the wind continues to blow. So if the wind continues to blow and continues to accelerate it at 2.3 meters per second, we expect it to be moving in the opposite direction. So now we're asked for a new final velocity. So final velocity equals v naught plus at, so same equation, same initial conditions, just we have a new time. So I have a positive 7.5 meters per second plus a negative 2.3 meters per second squared times 6 seconds. And if you plug those into your calculator, you get a negative 6.3 meters per second. So this does make sense because this means that the boat is blowing in the opposite direction. Now, if we want to know the average velocity during the 6 seconds, it's a uniform acceleration, so it's nothing more than the simple average where we add up the two velocities and divide by 2. So if it started off, if it had a final velocity of 6.3 and negative 6.3 meters per second, and it started off with a positive 7.5 meters per second, and I divide that by 2, notice that I'm including the sign of my velocity, my final velocity, I get a average velocity of 0.6 meters per second, which once again makes sense because roughly half the time it's going in the forward direction, the northern direction, and about half the time it's going in the southern direction, and on average it's going more towards the north, and that's what it means. Now, if we want to figure out the boat's displacement, we have average velocity, so we're looking for our delta x is our unknown. We have average velocity equals delta x divided by time. So if I cross multiply by t, my change in position is an average velocity times the time. So that is 0.6 or positive 0.6 meters per second times 6 seconds. So I get a 3.6 meters. Okay. Now, what if we didn't want to find the average velocity first? What if we wanted to go right from the equation to find how far it travels in that time? Well, what we can do is we can take a look at a velocity time graph to derive. So our object, we're going to just assume that our object starts at some positive velocity. So this is a v versus t graph. Some object starts at some positive velocity and it accelerates uniformly. Now our graph looked more like we had a negative acceleration, okay, because it was slowing down and then speeding up in the opposite direction. But let's simplify the case. So we have some initial velocity. Now we know that the area represents our displacement. And so what I can do is I could break this up into two simple shapes, the rectangle down below and the triangle up above, and I could say that the area of the rectangle, which is nothing more than a initial velocity, because that's where it crosses the y-axis, this is v naught, where it crosses the y-intercept here, times the time plus, okay, the change in velocity, so that change in velocity times the time, and then actually there's a 1/2 in front of there, it's a triangle, 1/2 base times height. And if we take a look, another way of rewriting the change in velocity, okay, we know that the acceleration, here, let me just erase that. We know that the acceleration, I'm going to come down here, the acceleration is equal to a change in velocity divided by time. So I can cross multiply, AT is equal to my change in velocity. So what I can do is I can substitute in this AT in for delta V, because we proved down here that they are the same. So if I plug that in, I'm going to rewrite this down here. I get delta X is equal to V naught T plus 1/2 times AT times t. And then rewriting this one more time, delta x is equal to v naught t plus 1/2 a, okay, times t squared. So what we did here is derive from a graph the fourth equation in your reference tables. And you will actually see this written as the delta x is broken up, and you'll see this written as x equals x naught plus v naught t plus 1/2 a t squared. Okay, and this comes from your delta x being broken up, x minus x naught, and then adding over the x naught. Okay, and that's your fourth kinematic equation. So go back up to the previous problem and see if you get the same 3.6 meters by plugging in the values into this. And a lot of the time your x naught is your starting position is going to be 0, so this cancels out and you're looking for your new position. And so your new position should be 3.6 meters. Okay, so we have a more complex problem here, and I'm going to introduce the fifth equation, and so you can certainly try to derive that on your own, and I can certainly help you kind of share how to figure that out. So when we are looking at a car, a really important quantity that car manufacturers give is a stopping distance. But in order for you to truly account for the stopping distance, there's also some reaction time where you're going at the same speed that you were traveling at. Yet, so in other words, before you hit your brakes, and then the braking period. So in order to figure out the reaction time, okay, or the reaction distance, so really our car is traveling along here, and for some time it's traveling at the same speed. So this is when it's traveling at a constant velocity. So here's our car driving along. You see what you're trying to avoid, which is over here. So for this distance, we are traveling at a constant velocity. And then once you start hitting your brakes, now you are slowing down with a uniform acceleration. So the fifth equation that's in your reference tables, it's v squared equals v naught squared plus 2 times the acceleration times your change in position. Now notice that of all the first 4 kinematics equations, this is the only one that has no time. So this is the timeless equation, sometimes referred to as the shortcut equation, because you can avoid using this if you don't want to have to solve for time. So let's set up the next problem, and then I'll ask you to kind of go through and solve it on your own. So the reaction distance, so when I'm dealing with the car moving at a constant velocity, I have average velocity equals your change in position divided by time. Now, since I'm moving along at a 25 meters per second, and that velocity is not changing, if the beginning of that reaction distance and the end of that reaction distance are the same, then 25 is my average velocity for the first time period. So I can find my reaction distance by taking my average velocity, multiplying it by how long it takes me to actually hit the brakes. And then the braking distance, I can write down my given information. So my initial velocity is 25 meters per second, and my final velocity is 0, since we're going to stand still, so to rest. And my acceleration is a negative 4 meters per second squared. Okay, and I'm trying to find my my braking distance. Notice no time. So my v squared equals v naught squared plus 2a delta x. So I can find my delta x here, I could find my delta x there, and then my total distance is just the sum of the two. So do the rest of A to find the total distance traveled, and try out B and number 3 on your own, and we'll compare answers tomorrow. All right, thank you for coming. Have a good night. Bye-bye.